Hi, and welcome to Optimization Problems 2. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is a part 2 of optimization. This is a part 2 of a calculus lecture involving the applications of differentiation optimization problems. It's for Math 1411 Calculus at UTEP. Chapter 3 from Larson's 11th edition Calculus. This is 3.7, Optimization Part 2. So, quickly going over some guidelines for solving applied minimum and maximum problems. This was also in the first half of the video. The problems we're going to see here are going to be a little more algebra intensive, a little more real world applications, and so the real world has some challenges to it. So, identify all given quantities and all quantities to be determined. In these examples, I encourage you to make a sketch and label things that you know. Write a preliminary equation for the quantity that is to be maximized or minimized. Are you looking for max area? Are you looking to minimize surface area? Maximum beam strength? What is it that you're looking for? We're going to reduce the primary equation to one having a single independent variable. It may involve the use of secondary equations. Determine a feasible domain for the primary equation, what makes sense in the real world idea. And then we'll find the desired maximum or minimum using the first derivative, sometimes the second to verify, using calculus techniques that we've already developed. So a solid is formed by adjoining two hemispheres to the end of a right circular cylinder. I think of these as the propane tank that you fill your little tank from, like U-Haul or wherever you fill up your propane tanks. So that's right circular cylinder, two hemispheres. The total volume of the solid is 14 cubic centimeters. Find the radius of the cylinder that produces the minimum surface area. Okay. The total volume of the solid is 14 cubic centimeters. So as soon as I see anything about volume, total volume of the solid, well, I'm going to lay that out. I want to know, find the radius that produces a minimum surface area, find the radius. So I need to minimize my surface area. So I kind of lay it out a little bit. What is it I'm looking for? What do I need? I need formulas. A right circular cylinder and a sphere, right? Two hemispheres would combine to make a single sphere, both in volume and in surface area. So our formula, the volume of this figure, the right circular cylinder, is pi r squared h. For the sphere, 4/3 pi r cubed. Surface area, as it turns out, check it out, derivative of volume is surface area. Yeah, so if you ever remember one equation and not the other, choose to remember volume. You can always take the derivative down and find your other values. So surface area is 4 pi r squared plus 2 pi r h. Notice the surface area, which we want to minimize. The surface area has two variables. One is r and one is h. Here's my secondary equation. I know the volume is 14, so I'm going to take this volume equation and solve for h in order to replace it here. Okay, so h, I'm going to subtract 4/3 pi r cubed, divide by pi r squared, simplify, that's 14 over pi r squared, minus a 4/3, the pi's cancel, r squared cancels, I'm left with an r. I'm going to substitute this into the surface area equation, and then take the derivative. Here we go. Get ready, get your algebra on. So my surface area, 4 pi r squared, plus 2 pi r, and instead of h, I'm going to replace it with 14 over pi r squared minus 4/3 r. Simplifying, 2 times 14 is 28. The pi cancels. One of the r's cancels, so I have an r in the denominator. 2 times a negative 4/3 is negative 8/3. Pi r squared. I have a pi r squared here and a pi r squared here, so 4 minus 8/3, that's 12/3 minus 8/3 gives me 4/3 pi r squared plus 28 over r. I now have a primary equation, surface area, in terms of a single variable r, and I can minimize this. The derivative will be 4/3 pi r squared, so times 2, 8/3 pi r, minus 28 over r squared. Remember, this is 28r to the negative 1. It makes finding the derivative easier. When the radius is 0, the surface area does not exist. So we know the surface area is undefined at a radius of 0, but a radius of 0 really isn't going to hold 14 cubic centimeters of contents, so that's a ridiculous answer in terms of real world. Let's solve for the surface area derivative equal to 0. I will add 28 over r squared to both sides. I'll cross multiply. I get 84 equals 8 pi r cubed, making r cubed equal to 84 over 8 pi, and of course I'm going to use that in a calculator. The cube root of 84 over 8 pi is about 1.49 centimeters for our radius. The radius that minimizes surface area, exact answer, the cube root of 84 over 8 pi. But if you wanted to round that to 2, 3, 4 decimals even, at 1.495 centimeters. Cubic centimeters make volume. Make sure you get your units correct. The units matter. Units matter. A wooden beam has a rectangular cross section of height h and width w. The strength S of the beam is directly proportional, got to think about that one, to the width and the square of the height by S equals K times WH squared. Directly proportional, so K is the proportionality constant of the width and the height squared. What are the dimensions of the strongest beam that can be cut from a round log of diameter 20 inches? Alright, let's break this down. A whole bunch of blah blah blah, okay. The dimensions, what are the dimensions of the strongest beam? The words strongest beam tell us I'm going to maximize my strength equation. Strength. The value K is a constant, but we have two other variables, W and H, that we must whittle down to 1. So, if we take a round log of diameter 20 inches, diameter's 20 inches, I can cut out the width and the height in order to make my beam. It seems as though we have a nice little Pythagorean relation here. We know that W squared plus H squared equals D squared, and D in this case is diameter of 20 inches. Since our equation already has an H squared in it, and so does our strength equation, let's solve for H squared. H squared is 400 minus W squared, so instead of S equals KWH squared, this could be S equals KW, and then we replace H squared with 400 minus W squared. You could choose to solve for W here, and then you have some radical in your strength equation. But nobody wants to deal with that. Always go with whatever the problem gives you. Don't be set on, I must solve for this variable. Go with what works with what you have. Now, our strength equation is kW times 400 minus W squared. I distribute, and I get 400 kW minus kW cubed. Taking the derivative, remember K is a constant, so 400K minus 3KW squared. I know that when the critical numbers will be when the derivative of the strength equation is 0. So set 0 equal to 400K minus 3KW squared. Add 3KW squared to both sides. Divide both sides by 3K. Notice the K's cancel out, so the constant of proportionality doesn't necessarily affect this. If W squared equals 400 over 3, then W is the square root of 400 thirds, which is 20 over square root of 3, and I can simplify that by rationalizing my denominator as 20 squared of 3 over 3. Now a couple of things to think about. 1, I only use the positive square root, but this is the width of a beam. I'm not going to have a negative width of a beam, so I take common sense into play here. And another common sense step, my dad, my whole family actually, works in the timber industry, and if I told my dad the width was 20 square root of 3 over 3, he would look at me and tell me that my education's showing. So why not just use what normal people use? 11.5 inches is the approximate for the width of our beam. I'm not saying my dad can't understand it, but my dad wouldn't be able to tell people how much to cut the beam for. Right? Let's use real values. Now, my width is about 11.5 inches. My height squared, remember from our Pythagorean relation, is 400 minus W squared. but I know that w squared is 400 thirds. So h squared equals 400 minus 400 thirds. That's 1200 thirds. Minus 400 thirds is 800 thirds. And when I take the square root in order to isolate h, I'll get about 16.3 inches. Now, is this a maximum? Is this a minimum? Is it strong? Is it weak? What's going on? The second derivative is negative 6 kW, which is negative for all positive widths. And if the second derivative is negative, concave down, I'll have a maximum. So I know this is a maximum. It'll be the strongest beam. Alright, a man is in a boat 2 miles from the nearest point on the coast. He is going to a point Q located 3 miles down the coast and 1 mile inland. He can row at 2 miles per hour and he can walk at 4 miles per hour. Toward what point on the coast should he row in order to reach point Q in the least amount of time? So he doesn't want to do the 2 and then walk it all and then walk down. That's going to take some time. We want to row towards our point Q and then we'll walk the rest of the way because we can walk faster than we can row. Let's see what happens. Let's break this into 2 parts. First of all, we have the amount of time he takes on water and then we have the amount of time he takes on land. We also know that distance is rate times time, so time must be distance divided by rate. And I have a whole couple of little right triangles here, so let's not forget Pythagoras. Now, on the water, I'm using blue. I know that 2 squared plus x squared equals d squared, or d equals x squared plus 4. Distance divided by rate equals time. I know that he can row at 2 miles per hour on water, so the square root of x squared plus 4, my distance, divided by my rate of 2 miles per hour equals my time in hours. On land, and if this entire distance is 3, but I'm rowing for a point x down the shore, then this will be 3 minus x, that's what's left. 3 minus x squared plus 1 squared equals d squared, or d equals 3 minus x all squared plus 1. This will give us 9 minus 6x plus x squared plus 1, and that 9 and 1 make our 10, and I've written it in descending order. The square root of x squared minus 6x plus 10. So my time on land, green, we're going to pretend there's grass there, square root of x squared minus 6x plus 10 over 4, the rate at which he can walk. I did take this nice image from WebAssign provided by Cengage. Homework problems matching Larson's calculus. Now, the least time, right? He wants to get there the quickest. He wants to take the least time. It means to minimize the total time. My total time is t, the time on water, plus the time on land. The minimum will occur at a critical number where t prime is either 0 or undefined. I find my derivative of the blue portion. Let's put that in blue. And I find the derivative of the green portion, the 1/4, of course coming from here, and the 2, the 1/2 out in front. Combining like terms, simplifying, doing all the things that we do algebraically, we'll end up with a t prime equals x over 2 square root of x squared plus 4 plus x minus 3 over 4 square root of x squared minus 6x plus 10. If you need to, take a minute, pause, check my derivative, check my second derivative, not the second derivative, my derivative of the second piece, and make sure my algebra works out in order to get t prime simplified. Now I have my total time, I have my first derivative. Solving for t prime equals to 0, I'm going to end up with a ratio if I subtract this first rational expression to the other side. And you know what I'm going to do? I have radicals going on here. I'm going to square both sides. When I square both sides, I'll get x squared over 4, x squared plus 4. On the right, if I square x minus 3, I get x squared minus 6x plus 9. And I square the denominators. 4 squared is 16. The square root squared leaves me the radicand. And now I'm going to cross multiply. 16x to the 4th minus 96x cubed plus 160x squared. Yes, these numbers are awesome. Equals 4x to the 4th minus 24x cubed plus 36x squared plus 16x squared. That's right, I have a couple x squareds in a row, minus 96x plus 144. Now, it'd be really nice to know where that comes from. Ah, yes, that works out for me. I'm okay with that. And when I combine like terms, I end up with x to the fourth minus 6x cubed plus 9x squared plus 8x minus 12 equals 0. We have our total time, solving the derivative of time equal to 0 using pre-calculus techniques, rational zeros theorem, a little bit of Descartes' rule of signs. We end up with x equals 1, or x is approximately negative 1.11. Now, this negative, rowing a negative distance, he would be rowing away from the direction he was trying to get to, so it doesn't make sense. This tells us our only solution is when x equals 1, and when x equals 1, he's going to aim for a point 1 mile down the shore from where he currently is, which will be 2 miles from the point Q along the shore. But since he's taking these diagonals, he's going to get there in the least amount of travel time. Optimization using some real-world situations. I hope you enjoyed it. Thanks for listening.